For the first time in the world, we were able to do this quantitative analysis of societal situations. But for overall as a field, we should see advances. So I'm also rooting for Oak Ridge to become number one. HPC is littered with cases of these failed startups and all the failed architectures that simply didn't make it, not because the hardware sucked, but because there was no software ecosystem.
From Orion X in association with Inside HPC, this is the @HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you again.
Great to be here. We have a very, very special guest today.
Yes, we do. We have one of the world's great computer scientists, Satoshi Matsuoka. He is director of the Riken Center for Computational Science in Japan, and he's also a professor at the Tokyo Institute of Technology. Satoshi, welcome.
Thank you very much. I'm really honored to be on this podcast, and hopefully we can have some great time.
Good. Thanks so much.
Satoshi-san, I wanted to start by congratulating you for the Purple Ribbon Award that you were honored with recently, and wanted to ask you if you don't mind commenting on that.
It's a great honor. It's one of the very highest prizes you can receive as a researcher, academic, or Olympic gold medalist for that matter. Mm-hmm. They also give them people like that. It's a recognition of your years of contribution to science, culture, sports, and so forth. And only like 24 people receive it each year, out of which like 8 are researchers. We have tens of thousands of those people. So it's very honored that my work has been recognized, but I think it's a recognition for the HPC field as well. I'm honored to represent the field to be receiving this award.
Absolutely. I think it is quite an honor for the whole community. Now, do you get to meet with the emperor?
Well, in normal times, but this is COVID time, unfortunately. So they canceled.
Oh, man.
They had to cancel the event, and all they gave me was a sheet of paper. In fact, I don't even have the medal. I'll probably tweet about it once I get the ribbon, but we'll see how it goes.
That's excellent. All right. The first topic is, of course, supercomputing, and you have a long history of it. But maybe we can start at the higher level and talk about the role of Japan in the supercomputing world and a segue into the award. How do you see that historically as well as into the future?
Japan has always been strong at supercomputing. In fact, if you look at across all the fields in information technology and, ICT, communication included, supercomputing is one of the domains where we still possess international competitiveness, and other areas where, we trail like US or other like China, etc., far behind. But supercomputing, high computing is where we still are very competitive. Not only just series of machines we build, but also we got quite talented sets of people, researchers and engineers and companies that can develop science engineering applications at the very high end. So I think we believe this is really important going forward for the society. As we know, of course, IT basically is very important as the infrastructure for sustainability and so forth to sustain society. But the role of HPC is becoming ever more important because, we have to simulate, do the AI, we have to do all these simulations, digital twins in cyberspace and so forth. And all of these have basis in HPC. Yeah, so I think our competitiveness will allow us to sustain our competitiveness and also achieve SDGs in the years to come.
Now, with the ISC conference coming up and the new version of the TOP500 list, we're sort of assuming that Fugaku will still be the number one system.
Well, in some benchmarks, maybe, because it's not, there are several benchmarks that are important, including the TOP500. In some of the benchmarks, we may still retain our number one spot. Some of the other benchmarks, of course, these are, supercomputing is extremely competitive field. No machine stays on top for many number of years. There's always technologies advancing at a very rapid pace. And this time, if we expect the U.S. frontier machine by Oak Ridge, if they could submit the benchmark in time to become number one. But we don't know the status yet. So
yeah.
That does seem hopefully, to be yeah. In fact, personally, I'm hoping they'll become number one because as much as I like our machine to be number one again, because that shows progress. And it's good for us that we're number one consecutively, but for overall as a field, we should see advances. So I'm also rooting for Oak Ridge to become number one as well.
Well, that's very sporting of you. But tell us a little bit about Fugaku and its use of ARM, and what led to the decision to go outside of kind of the the HPC chip mainstream?
So Japanese supercomputing, if you look back many years ago, they've all been based on mainframe technologies. And in fact, the US does as well. All the Cray vector machines, or even Europe. So in the past, all these in the 1980s and up to the early 90s, a lot of these technologies were based on mainframes. So you got small number of nodes, low parallelism meant, but each processor is fast, being a vector processor. Then mid-90s came, the US kind of stepped into using commodity chips for massive parallelism. First workstation, then PC processors later on. This basically was a way forward because hitting the limits of making a single processor faster. So the dawn of massively parallel computing came about in the early 90s, and then progressed forward. Now up to Fugaku, which is now sports 160,000 nodes, or 8 million, almost 8 million ARM cores, which is an astonishing number. But still, Japan kind of remained a little bit Galapagos in a sense that although we started using commodity processors, at least for the national flagship machine, we still retained the use of not so much proprietary, but non-mainstream processors like x86 or ARM. So the previous K computer used SPARC, which was mainstream in the past, but now was fading away. And it's one thing to build a machine, but modern IT, all the applications are very complex and require significant amount of support from the software ecosystem. HPC is no exception. So being harmonious with the rest of the IT ecosystem is essential for software development and running of the application and establishment of services. HPC being no exception again. So that's why we made the decision to go ARM. Of course, the other option was to go to x86, but there were licensing issues. So, and high performance ARM became our target, and we worked with ARM and other parties for about 10 years. We have the machine that's up and running that right now, which is massive but very useful and very easy to program.
Okay, so it was certainly not a departure from you. That's kind of what you're saying.
Well, it was, but there was a big fight, in fact, because some people, when in the early days of Fugaku design, some people wanted continuation from K, meaning it would adopt the same ISA, the SPARC ISA, with the modified, customized SPARC ISA, because you obviously a lot of the software ecosystem had to be rebuilt. We, Weekend and others, we really stressed, if we are to have sustained not just a machine but sustained ecosystem, we really need to go mainstream. So there was a big argument, maybe like 2012, 2013, even within Fujitsu, that was supposed to build a chip. But finally, the ARM camp won out. So that was a victorious day in some sense for not just for us but for Fugaku, and I think that's part of the success of Fugaku, that really is buying into the mainstream software ecosystem.
Was there something that you could not do with SPARC that you could with ARM? Because with K Computer, you basically had a very nice architecture and already a lot of software developed. The reason I ask is because I personally was in favor of SPARC. I thought, so I used to be at Sun, and I'm biased, but I also thought that you own it and you got all the IP and it makes sense to just build on top of it.
Well, not to put down my old friends who used to be at Sun Microsystems, who now everybody. SPARC was a fine processor, no doubt. I used the first SPARC Station. SPARC Station 2 was my desktop essentially in my early days of my career. So I have no objections against.
Absolutely, absolutely.
It was just fine risk ISA. Having said that, because of the various, I would say, business and a whole ecosystem climate as a whole in IT, it did, it's kind of lost its battle of being a mainstream, ISA, the overall ecosystem. So, there were other ISAs like IBM PowerPC, Power and PowerPC, there were Alpha, Deck Alpha, the plethora of various ISAs. But in the end, as we converged into the days of PCs, not only PCs, but these not just embedded devices, but smartphones, tablets, and cloud and so forth, we just converged into two ISAs, x86 and ARM. It only makes sense to buy into either one of them because at the end of the day, of course, in performance-wise, it really doesn't matter which which ISA you adopt. It's really about the software ecosystem, availability of software. And people usually, there's a lot of people who just aspire, especially hardware people. Again, they're fine people, but they sometimes come up with these funky hardware which has no software ecosystem that just die. If you look at HPC over the history of time, HPC is littered with cases of these failed startups and all the failed architectures that simply didn't make it, not because the hardware sucked, but because there was no software ecosystem. So
Right.
we took that lesson, and you just had to buy in. And with regrets, we ditched SPARC and we bought ARM. Yes.
I think it's definitely true that the community involvement with ARM is significantly bigger now.
Yeah, and you can say that. In fact, it's ARM SVE, so it's not just AC4FX which drives Fugaku. But now many companies and those who will embed their chips not only in these mobile devices but in the cloud, like Amazon Graviton 3. NVIDIA has the Grace chip, which will no doubt go into the cloud. Ampere has their own processor, which may go into other hyperscaler clouds. Fujitsu is now designing a new version which will go into the cloud, again with some SVE functionality. So, all the software ecosystem we have developed and also the community jointly are developing right now will drive this massive ecosystem, which will proliferate not just on a single machine like Fugaku, but throughout the cloud ecosystem. So a lot of our applications that we develop, for example, will run fine on those machines and very fast. So I think we're making the right decision. And in fact, the fruit of our decision will even be greater in the next several years.
Shaheen, whenever Fugaku comes up, Shaheen has mentioned this several times to me, that he sings the praises of Japanese supercomputers and Fugaku.
Okay.
It's so well balanced. Shaheen, I've heard you say that many times.
It's not just well balanced, but also physically beautiful. The K computer was just, you could stare at it for hours, and it was just beautifully done.
Well, yeah.
And I just love that. I think that shows, and then on top of that, it remains on the top 10 for decades.
The K computer.
The K computer was HPCG. It just would not let go of that benchmark. It was just so good.
Yeah, it has a big fight with newer machines, but yeah. Well,
yeah, and Fugaku looks exactly the same way. And I think in terms of it's being general purpose and it's being balanced and easy to program, and it just looks one end of the spectrum in my mind.
Well, yeah, of course, that was our objective, because we had to, in some ways, a lot of these codes, of course, are modernized. We ran the co-design program with Fugaku. And of course, there are certain hardware peculiarities, like long vectorization and so forth, that you still have to tune your code. It's not, you can run stuff, but, to get maximum performance, it's not that you're completely labor-free. People still do have to do a lot of tuning to get max out the capability of the system. That said, Seymour Cray basically once said it's the bandwidth. It's not about the flops. It's about bytes per second. It's about the bandwidth in the system. And if you look at many applications, in fact, we've done some formal research on this and published several papers, says that there's still a lot of these real applications that constitute simulations of certain forms to realize digital twins is bound by memory transactions and not so much by compute. There are a few that are compute bound, but most applications are bound by memory bandwidth. If you look at a lot of these processors, they're more emphasizing more flops these days, but not increasing memory bandwidth to the maybe except for GPUs, but normal CPUs are not increasing memory bandwidth that much. Well, they are, but not to the extent of AC4FX. And in fact, they're not adopting. It's been 4 years since the inception of AC4FX, and still no other mainstream CPUs have adopted high bandwidth memory, HBM2, as a memory technology. GPUs have, of course, but no other CPUs have done that. Intel is supposed to, have announced their next generation, Sapphire Rapids, with HBM2 last year or so. But they still haven't. Yeah, so being balanced, or it's really about analyzing your applications and making sure you make the right investments. The counterpoint to this is, if you look at the AC4FX chip, the cores are a lot smaller, let's say, compared to Xeon. So that means, for the integer performance, it's not as good as Xeon. So you really have to make sure you're not bound by some, integer bottleneck. That's where this, for example, tuning occurs. But once you do that, this massive memory bandwidth really kicks in, and you get several times faster application performance than a comparable Xeon. Yeah, so we've made a lot of effort to make sure that the machine does what it's supposed to do, is to really drive real applications.
So speaking of real applications, what are some of the uses that you've seen with the Fugaku system in recent times that you could share?
Yeah, well, of course, Fugaku being, like you say, general purpose, it just covers this plethora of applications from all around. But I'll maybe note two things in the interest of time. One is the biggest difference we see, of course, it covers everything from medical, pharmaceutical things like environmental, basically a lot of the sustainability goal type of applications, environmental from like climate change and things like that long term, and also short term weather predictions and earthquake predictions, things like new energy, all the way from huge wind turbines, 300-meter wind turbines, to storing this material studies on more efficient batteries and also better transmission technologies in the grid, to manufacturing, all the way from very small molecular structures for, let's say, like high temperature heat resistant polymers, all the way up to building huge tankers and ships without, for realizing for the first time a virtual pool instead of wind tunnel, virtual pool for designing ships. So it goes all around, and we're getting tremendous number of realistic results that are groundbreaking. Now, compared to K computer, the predecessor, it's not just my perception, but also everybody seems to have this similar perception that Fugaku, the fundamental difference between Fugaku and K, although similar programs are being executed, is the fact that K was more of a demonstrator machine. Although it was the fastest in the world 10 years ago, it didn't have enough capabilities to do, I would say, production in terms of really running a whole bunch of stuff and optimizing or searching for the best answer, because you can only do single shot runs at scale. Whereas for Fugaku, it's about 50 to 100 times faster compared to K. So now it's allowing people, the scientists and engineers, to do, I would say, real science and development as compared to K. They have this groundbreaking applications, and they can run numbers of instances of them continuously, such that they get groundbreaking results for real. So this seems to be a fundamental difference between K and Fugaku. The real results, game-changing results in the application space are being derived. One such area is, which we recently won the Gordon Bell Special Prize last year, was the application of the overall technologies to COVID. And of course, there are lots of anti-COVID applications running on Fugaku. One particular one was simulations of aerosols and how it spreads in the room, and how it's inhaled, and how it infects you. This was groundbreaking in that the application was never designed for COVID, but it was basically, initially the application was being developed for K and also for Fugaku for many years to simulate things like engine combustion, combustion in internal combustion engines. But then one of the researchers suddenly got the idea, he was not an expert in epidemiology at all, but suddenly got the idea that, hey, with people coughing and they're spewing these droplets and aerosols all over, this is exactly what injectors do in engines. It's the same physics. Yeah. So what they were able to do is take exactly the same code, even of course tune the parameters, because in engines the gasoline or the diesel fuel will burn, but combust, but you have to take that component out. Other than that, it's the same physics. So so the particles, for example, it's really meticulous. And that, for example, the particle, as they travel through the air, it evaporates. You have to simulate stuff to that resolution. It's not just simple CFD. So they were able to notice. And the other groundbreaking stuff about this particular simulation technology was it was able to generate detailed digital twins of the societal situations in matters of minutes. Because if these CFD applications, especially with unstructured mesh type of solvers, in commercial packages, for example, it's one thing to solve it, but to generate a CFD mesh in detail from, let's say, your CAD data will take weeks. But we're in this dire emergency situation where people are really, panicking because they don't know, because these aerosols are invisible. They don't know whether they should be wearing masks. They don't know whether they should ventilate, and well, maybe they can, but what's the most effective way? Am I in danger? There's no quantitative assessment of your risk, of what the risk you're under, because it's all invisible. So for the first time in the world, we were able to do this quantitative analysis of societal situations with respect to droplets and aerosols in a quantitative fashion. Of course, matching with reality, we check our results, but matching with reality, but do, hundreds of, in fact, more than 1,000 societal situations, over the course of a year. And then we announced every time we got great results, we were able to announce this to the public, and and then got TV and internet coverage, and basically it became a government policy, and basically saved a lot of lives in Japan and all the world. But again, this goes back to both the application development we have been doing and serendipitous usage to aerosols. But the amount of compute we consumed for that application was something like 20 million node hours, which is about the same quantity of compute available on the second tier, the top level second tier supercomputer in Japan. So basically, you had to take some, this a supercomputer, which is still, very powerful, tens of petaflops, dedicate that for a single year to this droplet aerosol application. We spent the same amount of compute time as that, effectively. Of course, the Fugaku is faster, so got it done a lot quicker. But this really testifies that we were able to have sufficient quantity of compute, coupled with these advanced simulation, provide real solutions to society that was really saved lives and also eased the impact on the economy. So
that's great. I've shared this with Shaheen in the past that I think if we're talking about the general public, I think supercomputing is kind of an unsung hero of dealing with COVID in terms of developing a vaccine and some of the scientific work that you all were doing as well.
Well, fortunately, I shouldn't say fortunately, because the whole COVID event was very globally unfortunate for many people. But for us, of course, it allowed Fugaku to be recognized by the general public in a very positive way. In fact, it was really interesting because, because it was carried all over in the news, everybody, we did the survey, 70% of people we surveyed know Fugaku in general public. Right? So, which we're very proud, because I don't think this has ever been replicated in any of the other countries that, your flagship supercomputer in any country is recognized by majority of the public. So right. That's great.
Yep.
But also, the public has gained trust in what we, they demonstrated trust in what we do. So it's really the professionals who question us, and for a very valid reason. I mean, are your simulation results correct? How did you validate your simulation? Well, what are the methods used? Of course, these are obvious questions that if you're a professional, you'd be asking. Of course, we have answers for those, and we have confidence in the results. But the general public, when we say this is a simulation results, these are simulation results from Fugaku. And right away, they believe in this. They have trust in science. They have trust in science done by supercomputing. And that really changed their social behavior. So, we're really, I was really, impressed and, by the fact that, supercomputing has reached this level where, general public has scientific trust, and they would entrust it to change the behavior to the extent to, protect themselves. So
that is such a profound contribution to society in general. Just wonderful. Very, very nice.
I remember in 2020, say in the summer, there were predictions that we'd have a vaccine by the end of the year, and lots of people were very doubtful of that. But I really was very optimistic, because I see all the literature and all the news and blogs and announcements coming out about what HPC was doing to work toward a solution. So certainly it gained my trust.
Yeah,
absolutely.
Well, still, it's very difficult to simulate, very large molecules like antigens. So yeah, so we're a lot of people, including us, are working on it. Yeah, still.
So Shaheen, should we move toward maybe a future look at supercomputing?
Yeah, good segue to talk about the future of supercomputing. As we know in supercomputing, as soon as you're done with one, the next one starts. So what could you share about the next project, number one? And number two, just how do you see the future of supercomputing shaping? I have seen talks and discussions from you about the specific architecture of supercomputing as it relates to homogeneity of nodes and
Oh, yeah.
the productivity of applications and the challenge that we have in terms of providing performance for one single task as well as for an entire workflow and an entire programmer community. Let's discuss
Yeah.
that a
So,
bit.
building machine, well, I think this is across, even true in any sort of engineering field. A machine which comes to fruition as a concrete entity is like a work of art, right? So you design it, you build it, it's there. But like you say, it's a snapshot of your best effort at it, usually. But as soon as you build it, you say, okay, I could have done this better. I could have done this better. You have lots of regrets, which it's always easy and it has an afterthought. And even Fugaku, there are several things we know we should have done otherwise, but we didn't. It wasn't me. Of course, it was a whole team of people designing the stuff. But there are a lot of things in retrospect we knew we could have done, even at that time, even within the time frame of Fugaku's inception. So, lessons learned. And but like you say, when you look forward, of course, there'll be tougher challenges. As much as industry says the Moore's law, we can extend the Moore's law now with with UV lithography and a lot of new transistor structures and so forth. The difficulty is that both the power and the cost reductions are not as dramatic as it used to be. So before when we had lithography reductions, we could also expect reduction in power such that transistor increase would be canceled out with the power reduction. So we have very similar power profile, but with the number of transistors increase, we can get performance that translates to performance gains. But no longer. It's no accident that that a lot of the modern GPUs that's been announced, both for the cloud and also supercomputing, and also for the consumer graphics. You see GPUs that are like 600 watts or 800 watts. I can grill my bacon and eggs with a GPU. Right? So I can. It's my home heater. So. But it's no accident because the engineers are pushing the limits as to how much transistors they can pack into a chip, and we're seeing increase because the transistor power consumption is becoming flatter with respect to lithography shrinking. So this means that we have to find ways to advance performance. For example, from K to Fugaku, we had about 50 to 100 times performance increase in a decade. But can we achieve sort of a similar magnitude of performance increase from Fugaku to Fugaku Next, we call, without incurring, let's say we get 50 times, 20 to 50 times performance gains, but it's impossible to attain that without 20 to 50 times increase in power. Then we need a nuclear power station. So because Fugaku already uses 19 megawatts, so times 20 is 400 megawatts. That's like a nuclear power station. So we really need to find ways to increase performance without this dramatic increase in power, coupled with the fact, as I mentioned earlier in the podcast, that a lot of applications are bound by data bandwidth as opposed to the flops, except maybe for the most recent neural network, deep neural network transformers, and a few other apps, but most are bandwidth bound. So our thought is to really try to build the next generation by achieving dramatic increase in the bandwidth without dramatic increase in power. And how to do that? Well, there are technologies that are already starting to be implemented, like 3D stacking, and also, very fast on-die chip-to-chip connection for chiplets, and also some of the advances in photonics for package-to-package type of communication. All of which, if we do the right architecting, our projection is it allows to attain significant, order of magnitude, more than order of magnitude increase in bandwidth compared to what you have, let's say, on Fugaku. So on a single package, right now, Fugaku is a terabyte per second. So ideally, we want to achieve more than, let's say, on memory bandwidth, more than 20 terabytes per second memory bandwidth. But it's, that's certainly, we've done some early assessments, and certainly that would be possible, but with restrictions. For the next couple of years, 2-3 years, I think people will still be on this limp-back flops or some sort of flops exascale bandwagon, because that was the objective, or especially for US and China. Of course, we nearly hit it. We could have hit it, actually, but we didn't. We made choice we would not, although we could have. And but of course, it's sort of exascale. We hit exaflop and reduced precision, so it's still an exascale machine by some definition. So this exascale flops bandwagon will continue for the next couple of years. But then people start realizing that, that's not what the true application performance is as we advance. There are very detailed subject matters with respect to this, which is kind of too long to be covered in this podcast. But basically, we want to increase bandwidth. But with other physical limitations, we really need to strong scale. That's the other thing, to strong scale, because we're not going to increase, let's say, the memory capacity and also achieve bandwidth at the same time. So we have increased bandwidth, but relatively smaller footprint. And for other reasons, like accelerating some compute-bound strong scaling applications like molecular dynamics, all the way to inferencing and deep learning. And all of these are strong scaling as well. So we are shooting for technologies, how to achieve a dramatic increase in bandwidth, memory bandwidth, system bandwidth, and reduction in latency such that we achieve strong scaling.
I have a couple of other questions, and hopefully we'll have time for them.
Okay.
One of them is that I read some material that you published at this point a couple of years ago about FPGAs and CGRAs, not just field programmable gate arrays, but coarse-grained reconfigurable architecture. Would you speak a little bit about the impact of that?
So, we believe that workloads can be categorized into like three. One is compute bound, flops. One is bandwidth bound, bytes per second. And then one is latency bound, microseconds to data access. Now, for bandwidth bound applications, we believe that general purpose processors with very fast memory of some sort, either CPU or GPU would be good. But and compute bound, you may have, lots of matrix engines like that's been now done by a lot of GPUs now. You have this tensor cores and all that, NVIDIA tensor cores and all the matrix engines, and that's the right way to go. But what about latency bound? And these are important classes of applications. For normal processors, be it GPU or CPU, you can make the algorithms latency tolerant, right, by hiding latency and so forth, or you make the algorithm fundamentally not rely on latency. But these are difficult and there are limitations. So fundamentally, we want, if we are to make the hardware to be coping with latency, basically the only way to do it is to kind of, be able to ship data from one compute to the other, with the smallest overhead, right? Instead of, you're loading stuff into register, from memory to register and compute, then you sort the memory, you load to another register on a different processor, that takes a lot of overhead. Rather, if you can ship your data from one ALU to the other ALU, that's the quickest latency you have. Yeah. So CGRA basically would be able to achieve that by basically connecting the compute units. It's a classic data flow architecture.
Right.
So for these latency-bound applications where we don't have the good abilities to accelerate either on a CPU or GPU, we believe it may have a role in those types of apps like molecular dynamics or certain types of inferencing in deep learning, very quick turnaround type of inferencing. You have to do like real-time systems because, for even, deep learning neural networks, the data flow fundamentally in the first place.
That's right. But also streaming, also some perhaps not typically HPC applications, except in really high bandwidth, just streaming data from a satellite or from a radio telescope, right?
Well, anything that requires not only low latency response, real time, that like the one you mentioned, it's not just so much bandwidth; it's the latency that's involved. Because a lot of so as the world moves towards applying HPC to digital twins, not just for postmortem or predictive analysis, but rather to do real-time responses. So, you have the digital twin in cyberspace, and you have a real entity, but somehow they're kind of connected. So, you actuate on the real stuff and you get a response from the digital twin. You do something on digital twin, you actuate the real world, vice versa. These kind of real-time connections between your digital twin and reality, you really need fast, low latency response. So, but that's the future we see, like metaverse kind of stuff. But it's not so much metaverse in terms of being able to do like office conversations. I don't think that's the best use of metaverse.
Right, right.
But rather to really replicate the entire city as a digital twin, and then really optimize, not only optimize system, but provide people with safety and also enrich people's lives in a real-time fashion. You have to have HPC in the background, but these HPCs will have to be real-time. So,
That's right.
for real-time portions of your compute, these CGRAs may have a role. So we're looking at it very closely to
That's
see if it
brilliant.
will be effective for the next generation.
How about quantum computing? How do you see that happening in the future?
Yeah, so we're very aggressively pursuing quantum computing. Weekend has another our sister Center for Quantum Computing, Weekend Center for Quantum Computing, RQC, and also RQC is a hub of this what's called a quantum hub in Japan that federates the quantum research in various institutions. So Weekend is really a centerpiece of quantum computing research in Japan, and we're also building physically a real quantum computer, and we collaborate. We at RCCS, we collaborate with these quantum people who are doing quantum computing. In fact, we have people doing quantum computing by simulating quantum computers on Fugaku. So either we can run a whole bunch of quantum computer simulators, which are really efficient and fast on Fugaku. So we have one of the fastest quantum computer simulators on a single node, but we have 160,000 of them, so we can run at the same time. Or we can exercise petabytes of memory in Fugaku to really increase the number of qubits we simulate. And we have various simulators for various purposes, depending on what people want to do. Because right now, of course, these quantum computers are not only, you don't have enough bits, but also they're NISQ, meaning they are so error prone, that they have so much errors that they cannot be really used for real applications. So on one hand, we're doing that. And our next generation, we hope to support the simulations of quantum computers in even a better way. That said, there are two problems. One is, of course, the quantum computers will not be replacing everything. In fact, right now, the number of the classes of applications we anticipate quantum computers to be having a quantum advantage over large-scale supercomputers is very small right now. It's very, very small. Right? Unlike the expectations of some, speculators who say quantum computer replace conventional computers. No, we say, okay, even not just us, but the quantum computer experts are just laughing at those predictions. Right? So, so quantum computers are good for something. Well, what is it good at? And we still need to increase the portfolio. And the only way we can do that is not only to devise new algorithms, but really to compare these to the best algorithms we can run on a supercomputer. Not just the ones that are good for quantum, but let's say you have material science simulations, and if you do quantum simulations in material science, how and when will it be better compared to the simulations done on a classical supercomputer? So we really need to investigate that to increase the portfolio. Even for those small sets of applications, it'll take years and years to reach the status where we'll have effective number of qubits to do things that were expected, like cryptography, for example. We need millions of tens of thousands, even hundreds of thousands, even millions of qubits to solve cryptography. And we're could be decades away from that. Oh,
Yeah,
well.
that's brilliant.
So as we look at quantum computers and try to help people build them, and evaluate them, we really need to, for production purposes, we need to hone in on what's the killer app for quantum.
Yes.
What's the killer app, right? So that we can foresee in the next decade or so in a real machine that will accompany a supercomputer. So so we're really looking at those seriously to see what can be replaced, because it's really a benefit for both camps, because if we know we can replace certain algorithms, and these algorithms are usually very compute bound, right? Then we can really, if we can replace certain workloads, compute bound workloads with quantum, then we can design our machine to be not so much emphasized on, let's say, the compute part, but we can really focus on the bandwidth part, which is, like I said, where the majority of applications reside. So there's quantum futures, there's non-quantum future, but figuring out what's the best mix moving forward will really allow us to progress our compute capabilities beyond what each of the individual computers can do. So
that's an excellent perspective. Thank you. If we have time, I wanted to ask a question about the earlier part of your career. Your fans know that you had a bit of a start in the gaming industry, so you were ahead of the rest of us with all the graphics and its impact on computing in this. And of course, you worked with the great Iwata-san, who went on to be the president of Nintendo, who left us too early and many years ago. But it's a period of your life that I have a personal interest, and I know your fans do as well.
Yeah, people say, I get some interviews, but most of these interviews have been in Japanese, so maybe I should do a more comprehensive revelation of my dark past. in the dark side. Yeah, well, no, it was a pleasurable time. I think really progressed my career as a good programmer, because these were days with like 8-bit, 16-bit processors, very weak graphics, and we needed to be as optimized as possible. So it taught me a lot of techniques to develop code very efficiently. So it was a good moment during the early days of my career. So there are many stories to tell, but just as a note, a couple of notes. So a lot of the early CBM, the PET or Commodore CBM games I had programmed, including the famous Invader game that people know.
Oh yes,
and I made a sort of a replica of that as much as I could with the restrictions of the PET hardware. And this was written fully in machine language in assembly. In fact, not even assembly, it was a hand assemble, pseudo hand assemble, and was only like 8 kilobytes but it runs the same. Essentially, I try to recreate the game experience as much as possible. There are other invaders, but I'm not going to criticize them. But I think mine had the best sort of a replication of the experience of the game you would have on the real Taito machine. So that was during high school many years ago, and it became very popular. But recently I tweeted about that because somebody tweeted, this was I played these invaders like significantly on PET and also emulators. I said, oh yeah, and I saw that and said, oh yeah, thank you. This is a game I programmed many years ago. A lot of people. Yeah, got a guy running a supercomputer center and was a game programmer.
I love it.
And in fact, it was great for me because, of course, got a lot of responses. But one of the people who responded, he was writing an emulator for the PET. He ported the PET emulator on an iPhone. So now I can play my old game, which like 40 years ago or something, on my iPhone. The only downside is it doesn't have sound because I put sound. But the simulator, some of the simulators on the PC, they have sound, but not on the iPhone yet. So I have to kind of play with silently. But it's been a great experience. The other experience I had was one of the programs I had programmed with Iwata-san was a pinball game for the early Nintendo, the first generation Nintendo system, which was called the Family Computer in Japan. What is called the NES in the rest of the world, and Nintendo Entertainment System. So, it was 6502 like Apple and CBM, and that's why. And so Nintendo came because they had a tabletop, you put in like quarters to play, Donkey Kong and those kinds of games, arcade games. But they wanted to build a home gaming machine, so they were porting their stuff over to this NES. Now, but the Donkey Kong and those arcade games, they were using a Z80, the Zilog Z80 processor, which was an improved version of the 8080. And 65, but the Nintendo, because of hardware restrictions, they were using 6502, which is a completely different processor. Very, very different. So they came, and so they lacked development skills, and so they came to this company that Iwata and others and founded. I was working there also part-time. And they came to us and said, well, can you program this? I said, oh, yeah, sure. Yeah, we're experts at 6502. And said, okay, well, maybe we'll give you a development environment. Oh, by the way, here's a sample code. So they gave us this sample code for the Donkey Kong, which they ported from Z80 to 6502. And we're looking at the source code. I said, and our first comment, this is probably the worst 6502 program we've ever seen. Nobody has programs like this. It's just horrible. And we immediately understood why they came to us, right? And, of course, again, they had no experience. And then this pinball, it was a joint effort by Iwata-san and me. And by the time I was studying computer science and also physics and so forth, so I applied many of my learned techniques from academic training over to the machine, over to the program as well. But then we had some Easter egg programmed into programmed without telling a Nintendo, which would display our names if you hit certain sequence of commands on the button on the controller.
Oh, nice.
Yeah, which obviously people do, but of course we didn't tell Nintendo. After a million cartridges were produced, somebody found this out. And of course, Nintendo was furiously.
That's a great story.
Yeah, and they said, "Well, no, this is just Easter egg. Nobody will know." Of course, the next version ROM, they of course took it out. So, what version of cartridge you have, but it's on the internet. And if you ever have a cartridge, you can try it out and see if it displays Iwata and Matsuoka. But it was memorable. I had lots of found memory. Iwata certainly he wasn't. It wasn't like he was a super programmer. A lot of people, there are a lot of fables on the internet saying that he was like this super programmer. Well, he wasn't really that kind of a hacker, but he was very orchestrated. He was a very, he was a methodological engineer. Mm-hmm. So he meticulously tried until he got perfection in his code, which was also similar to my taste. So that's why I think we worked together very well. So this kind of shows up in all his work that he had done. So I think that was one reason why he was able to propel Nintendo into the new heights, because I think he really wanted to, I think back in the background, he really tried, came up, a lot of people probably came up with ideas, and I think he would methodologically try every one of them to see which one's successful, and then try the one that seems the most viable. Not just go out and say, this is the best. Right? So
that's the way to do it.
Yeah. So again, as you say, we're really sorry we really lost him in the midst of, in the heights of his career. But
yes.
But I think his legacy lives on. And I think that being involved in the gaming world early on in my career, before I decided to focus on my PhD, and for some reason I became a professor.
Right.
Although I didn't intend to, but really helped me to, in the later parts of my career, to know how gaming processors are architected, and allow me to have very strong beliefs that these can be applied to HPC.
Mm-hmm. Satoshi, this reminds me of the movie Jiro Loves Sushi, and the relentless pursuit of perfection. I think he is, and I don't know if he's still living. The movie is a few years old, and he was already old at that time. But it is absolutely inspiring, just the level of meticulous attention to perfection that he had. That was just continuous. Even after it was perfect, he would make it even more perfect.
Yeah, well, we were, in the early days of gaming, we were forced to do that. In fact, I think people do that for games now, but now it's online, so people can make adjustments later. But in the days of ROM cartridges, right, these were the early days of gaming. Once you produce a ROM, that's it. Right?
Yeah.
If you have bugs, there's no way to patch. In fact, there's no way to patch it up, because there's no internal state in these machines. So you have to be perfect from day one. These ROM cartridges. Now, of course, there are a few bugs here and there, but because, for example, I remember one game I developed, and this was also a ROM cartridge for Nintendo, and I was writing my master's thesis at the same time. And it became very treacherous because as I was working my research, I had to spend, many sleepless nights trying to finish the thing. And then I finished and, was still a few months away from completing my master's, writing my thesis. So I said, okay, I'm going to stop now. This is my gaming development. This one's done. So I was totally focused on research. Don't call me. Okay. And then like 2 weeks later, like a month later, I get a phone call saying, we found a bug in your program. Can you come and fix it? And I'm like this totally entrenched in finished my master's, somehow trying to graduate. I said, okay, I got to come in. And this is really weird bug, which of course you never anticipate a bug, but this after many test runs, still there was this bug which was there. I won't go into details; it's complicated. It only shows up in very rare cases, but still a bug. So it took me like a week to fix it. Unfortunately, it was just before the ROM was being burned in, so it was caught just in time. So we really had to play the games ourselves. We had to test players, and we had to play it many times to weed out the bugs. But again, because there were no way to patch them, so we had to be paying attention to every little detail during those days. There's no patch 1.0.0A1 available for download. Yeah.
Amazing stuff. Well, Satoshi Matsuoka, just a real thrill and a great pleasure to speak with you.
Yeah, it was mine. Hope didn't go too much over time.
Thank you very much. Thank you for being generous with your time. We kept you way above what time you'd allocated to us, so very grateful for that. Look forward to our next opportunity.
Yeah, thank you. In several minutes, I have to speak to the RICAN president, so relaxing to opportunity to get myself relaxed before speaking to him. Yeah, he's my boss.
Brilliant. Thank you very much.
Right, thank you. See you. Talk to you again. Bye.
That's it for this episode of the @HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.